Okay, so I'm going to talk about a lot of the things that we've heard about this morning, basically about the redistribution of the mid-latitude ionosphere and the plasmasphere and all of these kind of conditions. The main point that I want to come up with to start out with is that cold plasma from the ionosphere and from the outer plasmasphere couples geospace, and you'll see what I mean. It goes every place, and it has lots of impact. Ground-based observations, which is what we've been doing for a whole number of years, at the foot of the field lines map magnetospheric circulation where this plasma goes. Subaurora polarization stream electric fields driven by the magnetospheric ring current are what are responsible for the formation of the bulk of the plasmasphere drainage plume. We can map this from the ground. I'm going to show you numbers of types of ground-based observations. I'm going to project those into the magnetosphere. Then I'm going to show you direct comparisons with in situ measurements with Themis. We've heard about some cluster observations, which are directly pertinent, and the Van Allen probes. Very importantly is this redistribution of this cold plasma material from the outer plasmasphere and from the mid-latitude ionosphere brings large quantities of ionospheric O+ ions to the magnetopause merging region, as well as to the cusp, where it can participate in lots of acceleration mechanisms. So this we all know. We know that the ionosphere is this little blue layer, and the magnetosphere is like this. And I'm going to talk about observations. Rod Heelis showed convection patterns here. You have to realize that all of those map out the magnetic field lines into the magnetosphere. And I'm going to show you a little bit of observations to show you the type of thing I'm going to talk about. Now, I've got an incoherent scatter radar background, and actually I've got a Yosemite background because it's cross-country skiing with Rick and Peter here in Yosemite #2 got me a job at Utah State working with the Chattanooga radar, which got me a job at Millstone Hill. And so here I am today. So I'm going to talk about the Millstone Hill incoherent scatter radar, which unlike Chattanooga sits under the plasmasphere boundary layer. When I was a grad student, I worked with Don Carpenter, and we looked at effects at the plasmasphere boundary layer, but he or we didn't call it that at that time. That had to do with relativistic particle interactions at the plasmapause, is what that was about. And that's where we are with the Van Allen probes these days. So this is Millstone Hill radar observations of the mid-latitude ionosphere in the evening sector. Just vertical profiles of ionospheric density on a logarithmic scale. The point is that it's structured. It's not a nice solar-produced and recombining ionosphere you'd think at mid-latitudes. It's mapping structure coming down from the magnetosphere. Important for what we're going to talk about later, you can take radar observations as a function of altitude, and you can just, I don't know whether my thing is going to work here too much longer. You can calculate F region total electron content by integrating those vertical profiles. And you can compare that with other observations to see how things map up. Now, this is my Chattanooga radar picture that Joe Dupnick and I worked, and Joe Dupnick worked me really hard, steering the Chattanooga radar to actually do latitudinal profiles of the convection electric field. So Rod Heelis says that these average models, aren't really what takes place, but this is what we could measure. The point here is this is our empirical Chattanooga 2-cell convection pattern, and Jan Soika then projected this, and it was presented at like Yosemite 3 or Yosemite 4 in magnetospheric equatorial plane using a current magnetic field model. The whole point of this paper, or this slide, is you can take ionospheric measurements and you can invert them and project them into the magnetosphere if they really map along field lines. This red region is the subauroral region where this subauroral polarization stream takes place, which is the source of the plasmasphere erosion plumes, which would be in this region over in here like this. And you can think of the erosion plumes as going out along these sort of convection things. If somebody has another pointer, I could use one because this one is not going to work too well. The forward button? Okay, great. Thank you. Thank you very much. So this will be important because I'm going to go back and forth between the point of view of ionospheric observations and what happens out in the magnetosphere. So the next type of observation I'm going to make a lot of use of is a more modern one, which is ground-based total electron content from the GPS satellites. There's 30 of them up here in orbits at about 4 Earth radii, transmitting down to thousands of ground-based receivers. Each ground-based receiver can see 6 satellites at any amount of time. Dual frequency means you can calculate integrated total electron content from the ground to the satellite. You can then project that into vertical TEC and make maps of total electron content over the surface of the Earth. So this is one I've shown many times. Here's the continental US. Each one of these 2x2 latitude, longitude boxes is independently calculated as the median of all vertical TEC measurements made through that particular grid point in a 10-minute period. White boxes don't have any. Over the continental US, when this was back from the last solar cycle, there were several hundred measurements in each one of these. And I'm going to show you this as a movie to show you the dynamics of what you can see with ground-based TEC. So this is the sun coming up over here. And look at this feature which is forming up over the northeastern part of the US of 100 TEC units, which is really, really massive. This is what we call the storm enhanced density plume. It was identified from the Millstone radar, as I'll show you over here like this. And it's something you see during all disturbances using ground-based GPS TEC mapping. Now, I've talked about mapping between the ionospheric observations and the magnetospheric. Ground-based TEC is the total content between the Earth's surface and 4 Earth radii. So I've made my 40-year career after Yosemite #2 on doing multi-instrument investigations of MI coupling. So here's a snapshot from the 1981 storm of ground-based TEC, showing one of these plumes which we had identified several years earlier, like a decade earlier from the Millstone Hill radar, as storm-enhanced density, ionospheric phenomena. I've just put some boundaries on it, on the edges of this, and I show where our radar scans, the Millstone Hill radar here, looking at vertical profiles of the Earth's ionosphere over this region. So this is what incoherent scatter radar sees as a function of altitude and latitude. Here's this storm-enhanced density plume, a nice, strong, integrated through here F region TEC of about 90 TEC units in a 20 TEC unit background. So we can see these things with incoherent scatter radar and with ground-based GPS TEC. The radar also sits here in Massachusetts and scans back and forth. And with incoherent scatter, you can see velocity as well as density. The product of those two things is number flux of ions. So this, on a logarithmic scale, is the Millstone Hill radar scan of velocity times density. The densities are all projected to being at like the 500-kilometer altitude level. And on a logarithmic scale, you have 2 orders of magnitude more ion flux right in the region, which is simultaneously measured with this GPS TEC plume. The line of sight velocities, or the overall velocity vectors, are in this direction. So the radar shows that the plasma in this is moving at about 1 kilometer per second and carrying a flux that is orders of magnitude above the background. Now, doing this inversion, we take this snapshot and these lines and just project them into the magnetospheric equatorial plane with the sun on this side, and you see a very nice representation of what could be considered a plasmaspheric erosion plume, with fluxes going out like this. Very nice. So can we now validate that picture using in situ measurements? I claim that we can with the Van Allen probes, with Themis, with a lot of the things that we now have at our disposal. So why is there this plume to start out with? This is, and we've seen the DMSP data was shown by Rod Heelis, and this is the edge of the plasma sheet precipitation, at least as seen at 800 kilometers. It doesn't have to be precipitating, it could be mirroring, and this sunward convection region, equatorward of the edge of the dusk sector plasmasphere, is what we call the plasma sheet precipitation region, is the subaurora polarization stream. This is something that's seen in very, very many of the disturbed DMSP satellite pictures. As to what we have here, this corresponds to the ionospheric trough from in situ densities, and as you'll see, it corresponds very nicely with where the storm-enhanced density and these plumes are taking place. So this is a picture that Jerry Goldstein came up with. It is just an image picture of EUV and FUV. It's not a snapshot. It's an artist's, Jerry's overlap like this. But this subauroral polarization stream would be right at this boundary of the enhanced ring current. The sun is down here like this, and the outer plasmasphere. This is an erosion plume where field-aligned currents in the region 2 region close with poleward directed ionospheric electric fields, giving you the westward flow at DMSP heights. But if you project that into the magnetosphere, a poleward field is a radially outward field, which will give you sunward convection and the erosion of the outer plasmasphere into the plume. So I'm going to get to the more recent observations very quickly. So here's a snapshot, multi-instrument snapshot. This is over the North and South American continent of log total electron content from GPS TEC. We have simultaneous, separated by 1 minute in terms of latitude, passes of 2 DMSP satellites, one through the equatorial region over here like this, which is where the SAA is, where you'd expect to have a lot of effects of penetrating field. What you have is no ionization there whatsoever. It's below the threshold of the density detector on DMSP. This is an equatorial hole. It's symptomatic of the redistribution of equatorial plasma up into what Gong Lu showed are these spread peaks of the ionization anomaly. The subauroral polarization stream is just shown up here like this. This particular satellite flies through this, flies through the SED plume in this region, and if I showed you velocities, and we have papers showing the DMSP observation through this, even with image EUV. So we see this redistribution of the low-latitude ionosphere, or at least the existence of elevated low-latitude TEC in the region where the subauroral polarization stream overlaps the mid-latitude ionosphere. So if we take that movie that I just showed you and we take one frame and we look in geographic polar coordinates at ionospheric heights, that plume that came up with 100 TEC units over Washington, D.C. at this time period in this superstorm, KP9 plus probably, extended back over the polar cap. This is a 20-minute snapshot of TEC mapped into polar coordinates. Simultaneously, here is the superdarn convection pattern, which is done combining superdarn and its model with 3 DMSP passes. Here's the DMSP pass at this time period showing the subauroral polarization stream and the regular sunward flow and the anti-sunward flow, showing that these plumes of ionization connect up through the dayside region, the cusp if you'd like, and give you this tongue of ionization that was mentioned earlier, going back over the polar cap all the way to the midnight sector. So now we're beginning to see the full extent of the redistribution of plasma during these events. So I'm going to show you a movie, and this one's going to show the formation of one of these plumes. This is January 17th, 2013. So it's about a year old, and you're going to see a tongue of ionization form, and from a point here, you're going to see patches of ionization go back over the polar cap. This is at a 10-minute per frame rate. So here, very quickly, as the event starts, you're going to see this storm-enhanced density plume to a cusp point, which forms here, and patches of enhanced total electron content being carried back, and the point here is it's patchy, back over the polar cap. I'll talk about that a little bit more later. So here's our snapshot that's been in a couple of the papers from the Van Allen probes that we've published lately. This is a picture of what I call is the ionospheric picture of the redistribution of the outer plasmasphere, or of the mid-latitude ionosphere. We have the erosion of the dusk ionosphere by the storm-enhanced density, by the subauroral polarization stream driven by the ring current. We go out into this area where we see this storm-enhanced density plume. Statistical studies have been published The Millstone radar sits here and has 50 years of measurements in this particular region. We go out to this cusp region where with SuperDarn or with radar or with GPS mapping, you can actually see this particular cusp point, and you can see the emission of patches going back over the polar cap. And this is the tongue of ionization region. And as you'll see in a few minutes, we can see this plasma coming up at altitude, meaning at 5 Earth radii. From this tongue of ionization, we can see the elevated plasma here using Van Allen probes or the radiation belt storm probes. So actually, we have 5 papers, recent ones, one in each one of those regions or in multiple regions, and I'm going to show you the results from some of those studies. So I'm going to introduce at the meeting the Van Allen storm probes, dual satellites in a wonderful orbit for looking at the outer plasmasphere. Apogee at 5.5 Earth radii. Apogee, the local time of apogee, very slowly going from midnight to dusk. So I'm going to show you dusk sector ones where we're in the Plume formation region. So here is a snapshot for the March 17th event. This is the same kind of one that I just showed you. Here's a plume. Here's the orbit of RSBP-A coming out like this over a certain time period. This is DMSP F18. There's a spatial temporal intersection point right near the edge of this at around 20 UT. If you map all of these orbits and all of this into the equatorial plane with the sun at the top, this region becomes a picture of a plasmasphere erosion plume. Oh, and here's the Millstone Hill radar doing a latitude scan over this region, all simultaneous. These are all simultaneous measurements, which would map to this region. Here's DMSP, and here's the Van Allen probes. And so there's going to be this intersection down here at about 22 UT. So what do we see when we take those kind of observations? So since this is a short talk, only 20 minutes, this from the electric field and the waves instrument on Van Allen probes, this is log density as a function of time as the Van Allen satellite flies out through this and goes outside of the plasma pause. This log bump is going through the outer edge of this forming plume. In situ electric field is measured by the Van Allen probes inside the plasmasphere, going through this bump, a nice two-humped region, and then out into this region, into the midnight sector. There's an overlap region of the high electric fields with the high densities. The product of those two is flux. This is sunward flux. So up here is the plasmasphere erosion flux measured in situ at an altitude of 4 Earth radii by RSBP-A. The flux in this region, in the region of this outer plume where you have this overlap of the saps with the outer plasmasphere, is 6 times 10 to the 11th meter squared second. Okay. And so down here we can take this whole thing and map it down onto the ground in terms of invariant latitude, the same things we just showed here. And here is the DMSP observations of the electric field mapping in, or to the flux, mapping very, very nicely in latitude to what's seen with the electric field. So fluence, that's been brought up. Here's the Millstone radar scan through this region, seeing the subaurora polarization stream, GPS TEC density, storm enhanced density, fluxes of about 10 to the 14th. But if you take the extent of the subaurora polarization stream with the GPS TEC, you get an afternoon sector fluence of 7 times 10 to the 25th per second, just with these sort of measurements. We also have the DMSP observations in the center of the polar cap. Here's the velocities. Here's GPS TEC, total TEC measured along the DMSP orbit. You can then do flux. We get flux measurements, and this is a sunward flux down here of about 10 to the 12th. But we can also integrate over this and get a fluence of 5 times 10 to the 25th per second. So we have measurements of fluence of plasma going this way and plasma going this way being nearly equal and very close to that magic number we heard from Cluster of 10 to the 26th per second. We see variable enhancements of the total TEC in the tongue of ionization during this event with an onset, with a cutoff, and we see variability in it, and we take this variability as the low altitude signature of variable day-side merging. The RBSP orbit then comes out here towards apogee. We have in situ measurements of plasma density enhancements on those field lines at apogee by two ways, by waves and by electric field boom potentials, showing that both RBSPA and RBSPB, separated by about an hour along the orbits, see this enhancement up until the time of a substorm dipolarization, when everything goes away and we begin to get midnight sector precipitation, which could be due to the formation, and the precipitation would be at energies that would be involved in chorus production. Richard Thorne's going to talk a little bit about low energy particles coming in during storms, during injections, coming into the inner part of the magnetospheric system, generating chorus, which then impact the energization of the radiation belts. We'll hear about those things tomorrow. So in my last 1 minute, Jerry, I'm going to talk about some neat stuff from just a couple of months ago. The formation of the Plume, with now the Van Allen probe orbits looking like this, with a spatial temporal coincidence near the equatorial plane out here at L of 5.5 of Themis E and RBSPA. This is in situ velocity. Jerry, at the beginning of this storm, where we see the undisturbed plasmasphere, at least as seen by this, we see a surge of 50 kilometers per second in this region, back along this part of the orbit. We see like 40 kilometers per second sunward flow along the edge of this plume. The interesting thing, and well, okay, so here's the Themis going outbound, very quickly going through the region, sees the plume, sees a highly variable electric field, 10 to the 13th per meter squared per second ion flux sunward in the plume. RBSPA is sitting out at almost at apogee in the outer edge of this plume for a 3-hour period. When you finally see the outer edge of the plume, we see 5 times 10 to the 12th flux. We see very large variability in the outer edge of this plume. The variability is very interesting to me. We see it for this entire region. This is near apogee. This is with 2 spacecraft near the outer edge of the plume. They're separated longitudinally by 2 Earth radii. These are electric field variations seen by the 2 spacecraft superimposed on top of each other, the same component of the field, totally synchronous in this region in the outer edge of the plasmasphere drainage plume. Older measurements with the Millstone radar in coherent backscatter mode. This is a paper we did a long time ago. see the subaurora polarization plume as this wide channel with very wave-like perturbations in backscatter in there, which correspond to 50 millivolt per meter electric field variations within that region. So, last thing, ion content. The radiation belt storm probe satellites have multi-species ion spectrometer. This is oxygen ions from about 0 volts up to 60 keV. In synchronization with these electric field variations, we see variations in the low energy and even in the high energy oxygen ions seen in this outer region. The oxygen ions from this we can use to do composition within the plume. They have protons, helium, and oxygen. So this is for number density within this plume region out like in this region. The ion fraction of O plus goes up from 5% to 20% within the plume, and helium isn't really changed. So a lot of interesting things with the Van Allen probes. This is what the oxygen looks like in this region, and this is number density again. Number flux, I'm sorry. We don't have the velocity taken out. This is the outer edge of the plume where we see very interesting things in low energy and high energy oxygen that are all related to this redistribution of plasma within the overall geospace system, which has lots of impact. Thank you.
Questions? Richard?
Yeah, would you care to comment on when the plume reaches the open field line region and you see the TEC continuing across the polar caps? I would have thought when you go into the open field lanes, the plasma would very rapidly flow out, expand, and densities should go down.
So
are you seeing the stuff mostly at low altitude in your?
So, well, one of the things, and so Bob Shunk is the person who can answer this very, very well. As long as the plasma is cold, motion along the field line is the same as the refilling rates due to pressure balances on that flux tube. It's very slow. So parallel motion without acceleration of the ions is very slow. If you can kick the ions up to a few thousand kilometers where they can get into, you know, a perpendicular acceleration mechanism, which would then kick them out, could then give you the several EV beams of these heavy ions that have been seen by cluster in that region. So there's lots of things, and Bob Strangeway has looked at modeling of some of these things too. So they don't necessarily get lost into the solar wind, but they very well might be on reconnected field lines, giving you beams going back down the tail lobe.
More questions?
Can you comment a little bit about the density measurements made by RSBP? How are those done? How reliable are they?
Okay, so we have two ways. Now you mean the cold plasma density? Yes. We have emphasis, and we can look at the plasma wave frequencies, which are directly proportional to density, and that's one calculation that's done by the Iowa group. The other group is John Wygant's group. The Berkeley group using the probe potential differences to take a look at this, and this is one that they've been using for a long time, and I showed the two of them superimposed on top of each other, and they're the same. So with those are all passive. Those are all passive.
Press the button.
Now it is. The green light means it's on. Suggest, in fact, that you aren't getting outflow on that particular case, because I've used your numbers, and you know the horizontal transport that gives you about the same amount of outflow over about 1,000 kilometers along track. So that it stays suggests that those ions, that part of the plasma, is in fact not escaping.
So I'm going to answer that in terms of it being lunchtime at the Yosemite meeting. You have a plate of sandwiches, and you have various people take a sandwich. It doesn't mean that the plate isn't still there and still doesn't have sandwiches on it. So you can have some of the ions get out into the magnetosphere through acceleration processes, and you don't have to have all of them
But
get out.
eventually the plate gets empty.
Eventually it gets empty. But in this case, it's just like here at these meetings, the plate gets taken from you very rapidly. So if you're not quick and grab some of the ions in that cusp region, you're basically seeing that. And so, Bob, so literally the point that I made in the beginning is the low altitude measurements map the foot of the field lines that are involved in this process. The fact that we see these low energy ions up at 5 Earth radii on those field lines with Van Allen probes suggests very strongly that some of that material is at 5 Earth radii. Where the rest of it is, we can't say with Van Allen probes because it's probably up in cluster space at many more Earth radii higher than that.